I'd like to introduce the second speaker of this afternoon session, Andrea Pedroso Kowacz, who is going to talk about global hypoellipticity of G-invariant operators on compact homogeneous vector bundles.
Thank you. First of all, I'd like to thank the organizers. It's been a very nice event so far. It's some great talks, really enjoying it. And also for the opportunity to speak here. So the subject I'm going to talk about is a little different from what's been spoken so far. I decided, so originally I was going to talk about the homogeneous vector bundles, but then I figured I would maybe focus on compact Lie groups. And then talk about well, it's sort of a consequence of results from this paper. And then also to introduce a bit more of the theory of the Fourier analysis on compact Lie groups, which can be a bit intimidating, but there's been some nice progresses, and yeah, I think it's pretty interesting. So this talk is mainly based on these two papers. So this one on homogeneous vector bundles, and then this preprint, recent one on arXiv, which just with some applications of these results and to the settings of Fourier multipliers for systems of operators on compact Lie groups. And okay, so first an introduction on Fourier analysis on compact Lie groups, which maybe some of you are not familiar with. So yeah, this is not a recent theory. There's a lot of work in this area, but recently there's this nice book by Kuzansky and Turunen where they developed another approach to this theory, which is fairly convenient to work with. So here's the book for more if you want to know more details about it. Okay, so just let's start. So along this talk, G will be a compact Lie group, and then we consider rep G the set of continuous, irreducible, and unitary representations of G. So since G is compact, these are all finite dimensional, so you can think of them as homomorphisms from the group to the set of unitary matrices of some dimension. Then in this set, we define an equivalence relation. Basically, if there is an invertible linear map which commutes both representations, and then the unitary dual is just the quotient of this set by this relation, and it is countable. Okay, and then so for any class in G hat, we denote by dig psi its dimension, which of course doesn't depend on the representative. Okay, so then we can define the Fourier coefficients of an integrable function. So we choose an element of the unitary dual, and then we define its Fourier coefficient. It's just this integral, and this is just a matrix. We choose a matrix representative. We can always do that. And then, so this is the coefficient. It's matrix valued. And well, here integration is with respect to the normalized Haar measure. And then, of course, this depends on the choice of representative. But this is ends up not being relevant, as will be explained. Well, so and then we have the Fourier inversion formula. It's like this, so we can recover f by this series, and then in this series we choose exactly one representative of each class, and then due to the cyclic invariance of the trace, this the the choice of representative doesn't impact this series, so that's what I mentioned before. And then this implies in all sorts of good formulas and identities. Well, the obvious example is just, so if we look at periodic functions on Rn, we can view them as defined on the n-dimensional torus. And then here the unitary dual can be identified with the exponentials. And then under this identification, we recover the usual Fourier series for periodic functions. Okay, another non-trivial example is SO3, which is closely related to SU2 and the tree sphere. So, okay, so in the case of SU2 or the tree sphere, we know explicitly the unitary dual is given by these elements, these representations. Its matrix elements are given by these in Euler angles, by this formula. These are known functions connected to Legendre Jacobi orthogonal polynomials. These constants are, yeah, I think there are some constants missing maybe, but they are known explicitly. Okay, and yeah, these are a bit weird notation here. The M and N, they range in this set, but they are, yeah, they're 2L plus 1 matrices. Okay, so back to general Lie groups. So the coefficient functions are smooth for the elements of the unitary dual. So we can extend the inversion formula, the definition of Fourier coefficients and the inversion formula to the set of distributions on G. Well, the coefficients are defined like this. Here the usual distribution duality notation. And well, equivalently, since the smooth functions are contained in L1, we can define them by duality. It's just equivalent. Okay, so also we have a quantization formula. So for a continuous linear operator acting on smooth functions, we decided define its associated global matrix valued symbol like this, which is very similar to the periodic case. So here, the operator is applied on each coefficient separately, of course. And then the action of D can be written like this. So here, yeah, this is the quantization formula. So D applied to f at x is given by this series, which is like it's like a pseudo-differential operator. So in particular, if D is left invariant, that is, it commutes with left translations in the group, then its symbol does not depend on x, and then we can write it, D applied on f is written like this. So the Fourier coefficient of D applied at f is just this product of matrices. And so in this sense, it's a Fourier multiplier. Here the fact that left translations has to do with our choice in the definition of Fourier coefficients, where we took the adjoint. If we don't take the adjoint, then it's with right invariant and so on. So yeah. Okay, so and then we also have, of course, the subleft spaces can be defined like this. So the subleft space of order S is a set of all distributions such that this series converges. I mean, if you remove this weight here, it's just the L2 norm, so it's the Plancherel identity. Here, this weight denotes it's given by this, and is the common eigenvalue of this operator corresponding to the coefficient functions of the elements of the unitary dual. And here is the positive Laplace-Beltrami operator on G, the LG. And also, as mentioned in our talk, the Hilbert-Schmidt norm of a matrix is given by this formula. It's just the sum of the square of all entries. Well, and then we also have, so of course, the union of all sublove spaces corresponds to the set of distributions. And then the intersection corresponds to the set of smooth functions. And then using the growth of these weights and the fact that the dimensions, they grow, they satisfy this identity, which comes from Weil's law. We have these characterizations for smooth functions. So function is smooth if and only if its coefficients decay faster than any polynomial on these weights. And it's a distribution if and only if it grows at most polynomially. Okay, so now for vector valued functions. So the main reference here is this work. So here everything is quite similar. So if f is vector value, we just define its Fourier coefficients like this. So here we have an n by 1 block column matrix with dxi by dxi blocks. This definition also extends to the set of distributions like this. So it's pretty much the same. We just focus on each variable separately. The Fourier inversion formula becomes like this, or it can be written like this, where the trace is taken component-wise. So for a continuous linear operator, we also can define its symbol like in this way. Here we are taking the dual basis on Cn and and Cm actually, but and well, anyway, we can recover the action of D with this quantization formula, which can also be written like before. But here we consider the block sigma d x psi is this block matrix with blocks given like this. Okay, so if D is left invariant, then its symbol also does not depend on x, and we have the Fourier coefficients of D applied to psi. Yeah, they're given like this, or by this formula if we use the big block matrix notation. Okay, and then so now to talk about global hypoellipticity. So just to remember, a pseudo differential operator defined on first a motivation. So about hypoellipticity. So a pseudo differential operator on an open set on Rn is hypoelliptic if on every open subset the following condition holds. So if P applied to U is smooth on this subset, then U is actually smooth. The global analog, of course, we dropped the subset requirement and we only ask for this to hold on the whole subset. Well, on a compact manifold, it only makes sense to talk about global hypoellipticity. So I bring here a more general version. So if we consider a compact manifold and then a continuous linear operator, it decided to be globally hypoelliptic if and only if this implication holds. So if you apply a p to a distribution and you get a smooth function, the distribution is actually smooth. And then, well, the vector valued part is commonly viewed in the context of systems, which is the main motivation of this work in this sense. Okay. So just some classic results. This result is probably older than this, but it's the first reference I could find. So a Fourier multiplier on the torus with symbol pic psi is globally hypoelliptic if and only if there exists these constants such that, so it's globally hypoelliptic if only if there exists constants c and k greater than 0 such that this inequality holds for all but finitely many psi, which is, well, it's basically using Plancherel's identity, and then you ask for fast decay, and yeah. But, okay, and yeah, so you can see this in this paper by Greenfield and Wallach. And then, well, before that, Greenfield and Wallach also have this paper. So this vector field on the two torus is globally hypoelliptic if and only if alpha is an irrational non-Liouville number. Here alpha real. So you see some Diophantine phenomena related to this condition here. And actually there is this big conjecture by Greenfield and Wallach that if M is a smooth closed connected orientable manifold and M admits a globally hypoelliptic vector field X, then M is diffeomorphic to a torus and X is smoothly conjugate to a constant Diophantine vector field like this. Okay, there is also this result by Huni, which will, well, I'm not going into details here, but we can also treat, which talks about non-constant vector fields here, and there is this sign condition that appears on the imaginary part. And then many other analogs for systems of compact Lie groups. For instance, this theorem by Rodriguez, which is restated here, and I'll go in more details in the next slide. But it's well, basically the analog. And then here's the main result, which you can draw from our other paper, which states that the left invariant continuous linear operator acting on smooth vector valued functions on compact Lie group, it is globally hypoelliptic if and only if a similar condition holds, but now you ask for the smallest singular value of this matrix to satisfy this inequality here of the smallest singular value of the symbol, since it's a matrix now for all but finitely many elements there. So for a system, it becomes a condition like this. So if you have a system like before, its symbol is given by this, and you get something like this. So, well, what's interesting is you can use this to get some applications and estimates. So, for instance, you have this lower bound on the smallest singular value of a complex L by L matrix, which comes from this paper here. And then, well, with that, we obtain that the system is globally hypoelliptic if there exists this constant C and K such that the determinant of the symbol in absolute value is greater than this. And then you also need to ask for that every PGI is of order less than this, or all dimensions are bounded, which, well, you recover the case of the torus at least in this case, and which gives you this corollary. And finally, for, well, the case of a diagonal system is trivial, but if you ask for a little less, if you ask for a block diagonally dominant, well, if your system is block diagonally dominant by rows and columns, which basically means that these numbers all are positive, then the small singular value is bounded from below by this, and then you obtain this result here. So you only need control on the diagonal terms, but then you need these elements to have order less than this, and then, yeah. So some nice applications. And, well, that's what I have to say today. Thank you.